What would happen if the stars you see in the sky were silently threatening life on Earth? About 14 million years ago, 15 massive stars exploded one after another, creating an enormous plasma cavity more than 1,000 light-years wide, heated to nearly 1 million degrees, enveloping the solar system we drift through today, the local hot bubble. The traces of those explosions still remain on Earth, buried deep within the oceanic sediments containing iron-60 like tiny fragments of memory, falling from faded suns. And at the very edge of that destruction, where the ashes still glow, new stars were born, a miraculous reminder that in this universe, life always begins from the remnants of creation. Can you imagine we are living inside the lingering breath of stars that once burned themselves just to exist? Right now, we will explore the story of the local hot bubble, a vast region of hot diffuse interstellar matter formed from about 15 supernova explosions. What secrets could be hidden within this star? There are nights when the sky feels closer than it should. A soft shimmer of invisible light seems to press against the edges of darkness, as if space itself were breathing. For decades, astronomers believed that what surrounded us was calm, empty, predictable. But in the 1970s, an unexpected glow began to whisper a different story. Sensitive X-ray detectors newly launched above the atmosphere started to record something strange. No matter where they pointed, the instruments found a faint wash of low-energy radiation spread evenly across the sky. It wasn't coming from stars nor from distant galaxies. It was everywhere around us. At first, no one knew what to make of it. The data seemed to suggest that our solar system was immersed in a thin fog of heat, something invisible yet warm enough to glow in X-rays. The idea sounded absurd. How could we be floating inside a hot cloud without even noticing? But the more they looked, the more the numbers refused to go away. Astronomers proposed a daring explanation: a cavity in the interstellar medium, a vast bubble carved by ancient stellar explosions. Inside it, the gas would be thinned to almost nothing, its few surviving atoms heated to 1 million degrees Celsius. They called it the local hot bubble, a structure hundreds of light-years wide, so diffuse that light could pass through it, unscattered yet so energetic that it quietly radiated across the entire sky. It was an elegant answer to a difficult mystery. And like every elegant answer, it attracted both fascination and doubt. By the early 1990s, new missions complicated the picture. Scientists realized that X-rays could also be produced when neutral atoms from interstellar space collided with the solar wind. Perhaps they argued the mysterious glow had nothing to do with a million-degree bubble at all. Maybe it was only the sun's breath, a local trick of plasma and magnetism. For nearly 2 decades, the debate drifted on. Every new measurement seemed to blur the line between possibility and illusion. Some researchers quietly abandoned the idea, calling it a beautiful myth born of poor calibration. Others held on, convinced that something real, something ancient surrounded us. Then in 2014, the question was finally tested. NASA launched the Diffuse X-ray Emission from the Local Galaxy Mission, or DXL. 2 high-altitude sounding rockets were sent above the atmosphere, each carrying detectors designed to separate local emission from cosmic background. As the data came back, the result was unmistakable. Only about 40% of the soft X-rays came from within the solar system. The rest, the dominant share, originated far beyond the heliosphere, streaming from a region of interstellar plasma, roughly 1 million degrees hot. The local hot bubble was real. Confirmation did not quiet the wonder, it deepened it. If the bubble existed, what could have created it? How could a region hundreds of light-years across become so empty, so hot and so persistent that it still glowed after millions of years? To carve such a cavity, something unimaginably violent must have occurred. Imagine 15 massive stars giants, many times the mass of our sun, living close together in a young cluster. Each burns fiercely for a few million years, fusing heavy elements in its core until the balance between gravity and radiation collapses. Then one by one they explode. Not randomly, but in sequence, their shock waves overlapping, reinforcing each other, sweeping aside dust and gas like a cosmic storm. The overlapping blasts sculpt a hollow, a superbubble, and in its wake a furnace of plasma continues to expand at 6 kilometers per second. Astronomers now believe this is what happened near us roughly 14 million years ago, the local hot bubble. The very space through which Earth travels each second is the afterimage of those 15 deaths. Our planet drifts through their echo. The thought is both thrilling and humbling. The night around us, cool and silent, is in truth the cooled remnant of a cataclysm. Every quiet sunrise over our oceans is in a way lit by the ghosts of supernovae. Still, science asks for proof, and in time the Earth itself offered it. From the bottom of the Pacific, Indian and Atlantic Oceans, researchers extracted layers of ferromanganese crust, slow-growing deposits that record chemical traces across millions of years. In those layers they found an isotope that does not naturally occur on our planet Iron-60. With a half-life of 2.6 million years, it is born only in the heart of massive stars and cast into space by supernovae. Finding it here meant that sometime within the past few million years, debris from nearby explosions rained upon Earth. Further analyses revealed two distinct peaks of this isotope. One between 6.5 and 8.7 million years ago, another between 3.2 and 1.7 million years ago. Two epochs, two showers of stellar dust. They matched the timeline of the proposed sequence of supernovae that could have hollowed our region of the galaxy. The match was almost poetic. Beneath miles of water in sediments older than humanity lay the fingerprints of dying stars, proof that our solar system once sailed through the ashes of cosmic fire. Those discoveries gave the hypothesis weight, but also raised new questions. Where exactly were these supernovae born, and what chain of stellar families left behind such a scar? Attention turned toward a nearby association of stars called Scorpius Centaurus. It is a loose cluster only a few hundred light-years away, filled with hot young suns and aging giants. Astrophysicists traced the motions of its subgroups backward through time and found that 14 million years ago, several of its members would have passed close to our current location. Their most massive stars, perhaps 8 or 9 times the mass of the Sun, would have ended their lives, then detonating in sequence. Each explosion swept the interstellar medium a little cleaner, feeding energy into the growing cavity that would become our local hot bubble. The story fits together like a quiet puzzle of light and time. 15 supernovae born in the same stellar nursery dying within a few million years of one another. Each one carving deeper into space, heating the gas, pushing the shock front farther out. By the time the last giant collapsed, the bubble stretched more than 1,000 light-years across. Today that expansion continues slowly, almost imperceptibly, 6 kilometers every second, a steady sigh through the thin medium of our galactic neighborhood. It is an ongoing breath from long-extinct suns, and somewhere within that hollow, the sun itself moves. Our solar system, circling the Milky Way at 200 kilometers per second, happens by coincidence to be flying through the very heart of this ancient wound. We are not the creators of the bubble, we are its visitors. Think of that the next time you look up. The empty darkness between stars is not empty at all. It is a cathedral built by explosions, its walls made of heat and memory. The faint X-ray glow that once puzzled scientists is the lingering hymn of that cathedral still resonating through the void. In the decades since DXL confirmed the bubble's reality, astronomers have refined their models, mapping its contours and comparing it to neighbouring structures. They find that its boundaries are irregular, elongated toward the galactic poles shaped by pressure and time. The plasma inside remains at roughly 1 million degrees, but its density is so low, about 100 times less hydrogen, than typical interstellar space, that a human spacecraft could cross it unnoticed. Only instruments sensitive to X-rays can perceive its warmth. What began as a faint anomaly on early detectors has become a vast landscape of understanding. We now know that superbubbles like ours are common throughout the galaxy, each a relic of clustered supernovae, each shaping the birthplaces of new stars along their edges. The Milky Way, in a sense, is a living tissue of cavities and filaments, scars of creation interconnected and breathing. Yet among all those bubbles, one holds special meaning for us because we reside inside it. Its warmth surrounds our home, its edges mark the boundary of the space we call familiar. Everything we know, the planets, the comets, the thin whisper of solar wind drifts within this luminous shell left behind by dying suns. And perhaps if we could see it with eyes attuned to X-rays instead of visible light, the sky above would no longer appear black. It would shimmer softly like a memory glowing from within, a gentle radiance, silent, ancient and kind. There is a silence in space that holds memory, a silence older than the sun, older than the dust beneath our feet. Hidden within that quiet lies a record of fire, a time when the region we now drift through was not calm and transparent, but alive with destruction. 14 million years ago, long before the first traces of humanity, Our part of the galaxy was home to a congregation of massive short-lived stars. They burned blue and fierce, hundreds of times brighter than the sun, gathering in loose clusters that drifted like sparks within the spiral arm of the Milky Way. Astronomers today believe that this ancient family of stars, the ancestors of the modern Scorpius-Centaurus association, would change our local universe forever. Stars of that size live fast. Their gravity squeezes hydrogen into helium at such an extreme rate that within just a few million years their fuel runs out. When that happens, balance breaks. The outward push of radiation can no longer resist the inward pull of gravity. The core collapses, and then in a fraction of a second the star detonates. A supernova is among the most violent events known to physics. In that brief flash, the collapsing star releases more energy than our sun will emit in its entire lifetime. Its light can outshine an entire galaxy. The blast wave races outward, shredding clouds of gas, compressing others, spreading newly forged elements across interstellar space. Iron, cobalt, nickel, gold, the materials that would one day form planets, oceans, and bones. Now imagine not one but 15 such stars, each one detonating within a few million years of the others, each one sending shock fronts racing into the same stretch of space, each explosion overlapping the remnants of the last, carving a shared cavity of hot plasma that expanded faster than any planet could orbit. 15 bursts of stellar death, 15 bellows of creation. That is the vision astronomers now hold to explain the origin of the local hot bubble. A chain reaction of supernovae beginning perhaps 14 million years ago swept this region of the galaxy clean of dust and heavy gas, leaving behind a void of extraordinary scale, 1,000 light-years across, still expanding at roughly 6 kilometers per second. When the first of these stars collapsed, the young solar neighborhood must have been dazzling. The sky would have burned with the light of multiple suns, each swelling and dying in cosmic sequence. If Earth had existed, then its nights would have been illuminated brighter than any full moon, the heavens awash with radiant streaks, ionized filaments and gamma flashes. But our planet had not yet taken its current path through this region. We were still elsewhere in the galactic disk. We would arrive later, long after the firestorm had passed, drifting through its ashes. The evidence for these ancient detonations does not come from imagination. It comes from the Earth itself. In the 1990s, scientists began to notice something unusual buried within the ocean floor. By extracting long cores of sediment and crust, they uncovered traces of isotopes that should not be there, radioactive atoms like iron-60 and manganese-53, which have no natural source on our planet. Iron-60 in particular is telling. It is produced only in supernova explosions. Its half-life, 2.6 million years, means it disappears quickly on cosmic timescales. If we find it in terrestrial sediments, it must have fallen to Earth recently, within the last few million years. 2 major peaks of this isotope have been discovered, the first dating between 6.5 and 7 million years ago, the second between 3.2 and 1.7 million years ago. Both align with models predicting waves of supernova activity in the Scorpius-Centaurus region. The radioactive dust that fell through our atmosphere during those epochs was likely the residue of stellar deaths just a few hundred light-years away. Deep beneath the Pacific and Indian Oceans, every grain of crust that scientists lift carries a message from those explosions. Measured precisely, the ratios of iron-60, cobalt-60 and nickel-60 form a kind of clock, a chemical timeline that marks when the debris reached Earth. And so the story of the local hot bubble is not only written in the stars, it is written in stone, buried under miles of ocean water. In 2016, nuclear physicist Anton Wallner led a team that analysed these isotopic fingerprints. They confirmed the dual peaks and noted something remarkable. The younger layer, the one between 3.2 and 1, 7 million years old, was spread over a wide time span, roughly 1.5 million years. That meant the bombardment wasn't from a single explosion, but from a series of them, a chain of nearby supernovae, each contributing dust and radiation to the same interstellar storm. Another research group, led by astrophysicist Dieter Breichwerd, traced the possible origins of these events. By reconstructing the motion of nearby star clusters, they found that the Scorpius-Centaurus association and its subgroups, Upper Centaurus Lupus and Lower Centaurus Crux, would have been the likely birthplaces. At the times of the isotopic peaks, their massive stars were positioned roughly 200 to 400 light-years from where our Sun is today. close enough to leave a mark but far enough not to sterilize the Earth. Their models even pinpointed 2 individual explosions that fit the evidence perfectly, one around 2.3 million years ago, another near 1. 5 million years ago from stars about 9 times the mass of the Sun. Each detonation would have injected a shockwave of charged particles and heavy elements into the surrounding gas, continuing to heat and expand the cavity our local hot bubble. As these supernovae fired in sequence, they did more than empty space. They transformed it. Shock fronts swept together the remaining gas into dense ridges the way ripples on a pond meet and rise. Within those compressed filaments, new stars began to form. The edges of the bubble became a nursery, bright, turbulent, alive. This is one of the most striking revelations of modern astrophysics. The death of stars does not end the story, it restarts it. Every supernova both destroys and creates, feeding the next generation with raw material. The heavy elements forged in the furnace of one star become the seeds of others. In time, planets condense around those new suns, and somewhere perhaps life arises built literally from the ashes of what came before. When astronomers simulate the expansion of the local hot bubble, they see this cycle written clearly in motion. 4 epochs of star formation have followed since its creation. Each corresponds to a ring of young clusters at its periphery, first Upper Centaurus Lupus, then Lower Centaurus Crux, later Upper Scorpius, and finally around 2 million years ago, the Lupus and Chameleon clouds. Each generation ignited at the edge of the shockwave as the hot gas pushed into cooler molecular clouds. It is as though the bubble itself were breathing, exhaling destruction, inhaling creation. But what of our Sun? Where was it during all this? Was it born inside the bubble, or did it wander in from elsewhere? Careful orbital reconstruction gives an answer. The Sun was not here when the fireworks began. Roughly 980 light-years away at the time, our solar system only drifted into the expanding cavity about 5 million years ago. By then the shock waves had weakened, the heat had spread thin. We entered not a furnace but a memory, a region still warm, still luminous in X-rays but quiet. Today the Sun sits almost at the centre of that structure. By chance, our home star occupies the calm heart of a storm that ended long before humanity began. We are in a sense the inheritors of a cosmic battlefield floating gently through the aftermath of explosions that once shook the very medium of space. And though we cannot see it with our eyes, instruments reveal its continued presence. The boundary of the bubble glows faintly in soft X-rays, its temperature steady at around 1 million degrees Kelvin. Its expansion persists slower now, like a ripple fading across a pond that has stretched too far to feel its own motion. Some scientists describe this structure as a superbubble, a term that might sound simple, but hides immense complexity. The local hot bubble is not a perfect sphere. It is ragged, asymmetric, torn by gravitational tides and magnetic fields. One side reaches farther toward the galactic north, the other opens into nearby cavities, hints of tunnels that may connect it to other remnants of supernovae. But those mysteries belong to later chapters. For now, what matters is understanding that everything around us, the quietness of the sky, the thinness of interstellar space, the faint X-ray whisper detected in our instruments, all of it is the residue of an ancient cataclysm. It is difficult to imagine such violence because we live in its peace. The energy of those 15 explosions has long since dispersed. The hot plasma that remains would not harm a passing spacecraft, nor would it scorch the planets within. Its density is so low that you could travel 1,000 kilometers through it and not strike a single atom. And yet even in that emptiness, the memory of heat endures. If one could step outside the solar system and look back, if human eyes could see in the X-ray spectrum, the scene would be haunting. Our star, small and golden, would hang near the centre of a vast translucent shell. The walls of that shell, faintly glowing uneven, would shimmer in blue and violet light, like the skin of a bubble drifting through a cosmic ocean. Beyond it, other bubbles would overlap, each one the echo of its own series of deaths. Together they would form a patchwork of cavities, a galactic honeycomb born from fire. To drift inside such a structure is to live within the evidence of time. The iron in our blood, the calcium in our bones, the gold in our rings, all were once atoms forged in the cores of stars that perished long ago. Their ashes fill not only the sky, but us. We are literally made of the debris that still glows faintly around our solar system. The local hot bubble, then, is not just a region of space. It is a reminder that everything which ends continues, that every silence once rang with thunder, and that even now, millions of years later, we sail through the afterglow unaware that our peace is built upon the memory of 15 dying suns. There are patterns hidden in the chaos of the galaxy, lines that cannot be seen but can be felt, faint geometries written in light and dust. For decades, astronomers mapped the Milky Way as if it were a flat disk, a spiraling pattern of gas and stars. But when the data from the Gaia Space Telescope began to arrive, that illusion started to dissolve. Gaia, launched by the European Space Agency in 2013, has measured the precise positions and motions of more than 1 billion stars. Each observation is a coordinate, each coordinate a story where a star was where it is and where it is going. For the first time, we could watch our cosmic neighbourhood in 3 dimensions, not as a painting, but as a living structure in motion. Among those who read the data differently was Catherine Zucker, an astrophysicist at the Harvard-Smithsonian Center for Astrophysics. In 2022, her team set out to reconstruct the local history of our galaxy's interstellar medium. They took decades of distance measurements, combined them with data from Gaia and other surveys, and built a dynamic 3D model of the gas and dust surrounding us. What they discovered changed the way we see our place in the Milky Way. The model revealed that the local hot bubble, the vast cavity carved by ancient supernovae, is not an isolated void. It is the central feature of a much larger landscape, a complex web of gas clouds, filaments, and star-forming regions extending for hundreds of light years. And on the shimmering edge of this enormous cavity, something extraordinary happens. Every known cluster of young stars within 500 light-years of the Sun lies exactly along the surface of the bubble. Not scattered randomly through space, not floating aimlessly in the galactic plane, but arranged like glowing beads along the curved shell of an invisible sphere. It is as if the bubble itself sculpted them. When the first supernovae created this cavity millions of years ago, their shockwaves would have swept through nearby molecular clouds, compressing them, squeezing them like ripples that pile up on a shoreline. In those compressed ridges, gas cooled, condensed, and began to collapse under its own gravity. Out of that collapse, new stars were born. The very edges of destruction became the cradles of creation. The pattern is astonishingly consistent. The upper Centaurus lupus and lower Centaurus crux associations appear on one side of the shell, tracing the first generation of stars born from the bubble's expansion. Farther along its curve lie the upper Scorpius and Corona Australis regions, younger still lit by newly ignited suns less than 5 million years old. And still farther faint clouds, the lupus and Chameleon complexes, show signs of star formation continuing today. In every direction the evidence is the same, the edge of the bubble is alive. Zucker's team visualized this structure using advanced 3D rendering. They traced the flow of interstellar material, the arcs of dust illuminated by background starlight, the distribution of hot plasma seen in X-ray emission. The result is a cosmic sculpture, an immense hollow surrounded by ribbons of glowing gas, its surface marked by clusters of newborn stars. And right at its heart, almost perfectly centered, floats our sun. The image is almost poetic. Our solar system is not drifting through emptiness. It is drifting through a story, the echo of death, the consequence of birth. Astronomers call this idea triggered star formation, when the death of one generation of stars provides the physical push that creates the next. The expanding shock wave from a supernova moves through cold interstellar gas, compressing it until gravity takes over. The bubble becomes both tomb and womb. If you could travel across light years and look back upon this region from afar, you would see the Milky Way's arm peppered with cavities like this, a honeycomb of super bubbles each, the legacy of clustered supernovae, each rimmed with bright arcs of star-forming gas. Our local hot bubble is just one of many, but it is the one we know most intimately because we live inside it. To understand its rhythm, Zucker's team traced back the timeline of star birth within the surrounding regions. They identified 4 main epochs of stellar formation, roughly 16 million, 10 million, 6 million, and 2 million years ago. Each wave corresponds to a new set of supernovae and a new generation of stars forming at the edge of the expanding shell. In essence, the bubble itself has a heartbeat, a pulsation of creation every few million years. The process begins with death. A massive star explodes, sending a shock front outward at thousands of kilometers per second. The hot plasma expands, collides with denser clouds, and piles them up. Those dense clouds cool, fragment, and collapse into hundreds of new suns. Some of those new suns are massive, and they too will explode, sustaining the cycle. Life and death alternate generation after generation, each one painting a new layer onto the surface of the cosmic sphere. At this point in the story, speculation and observation merge. Scientists can measure the motion of these clusters, their ages, their distances. They can simulate their evolution through galactic time. But behind every number lies a mystery. Why is the pattern so precise, so beautifully coordinated? Is it coincidence, or is there a deeper symmetry at work, a natural rhythm in the galaxy that synchronizes these waves of creation and destruction? Some theorists suggest that these superbubbles interact through the galaxy's magnetic field. As they expand and overlap, their boundaries press against each other, shaping the flow of charged particles. The pressure at those intersections may determine when new stars ignite. Others propose that the turbulence itself, the chaotic motion of interstellar gas, naturally organizes into bubbles and filaments, like foam rising on the surface of the sea. In that analogy, our local hot bubble is a single bubble in an ocean of them, part of a frothing galactic sea. There's beauty in that idea, to think of the Milky Way not as a static collection of stars, but as a living organism breathing in cycles of explosion and calm. Every burst of violence followed by a quiet expansion, every silence followed by light. The Gaia data confirm that the Sun itself was never part of the original bubble's creation. It likely formed elsewhere in a different molecular cloud and drifted into this region about 5 million years ago, a cosmic wanderer entering the empty cathedral of past destruction. By extraordinary coincidence, it now sits almost exactly at the centre of the structure. To live inside a void made by other stars' deaths that is our inheritance. If we could hear what space sounds like here, the bubble would hum in frequencies too low for human ears. A soft, omnipresent resonance of plasma and magnetic fields like wind moving through hollow metal. Every charged particle that flows from the Sun, every whisper of the solar wind interacts with this invisible background tracing paths shaped by its million-degree gas. Our heliosphere, the magnetic shield that wraps around the solar system, presses gently against the bubble's plasma, merging two worlds of energy into one. In that borderland between heliosphere and bubble, cosmic rays are deflected and filtered. It's possible that without the protective cushion of this hot void, the solar system would be bombarded by far more interstellar radiation. Ironically, the very structure born of destruction may now serve as a buffer that keeps us safe. Zucker's visualization gives this region a tangible form. If you were to step outside the galaxy and look back toward the Sun, you would see the bubble's shell glowing faintly, a filament of gas shaped like a vast sphere, nearly 1,000 light-years wide, shimmering in ultraviolet and soft X-ray light. Along its edges, clusters sparkle Upper Scorpius lupus corona, Australis chamaeleon, each one a bead of new life on the scar of an ancient wound. The geometry is mesmerizing. The Sun rests in the middle like the nucleus of a cell. The surrounding stars trace its membrane. If galaxies are organisms, then perhaps this is how they grow, through cycles of damage and repair, through structures that remember their own making. From a philosophical point of view, there's something quietly reassuring about this pattern. It reminds us that destruction is not chaos. It is structure waiting to be revealed. When a star dies, it gives shape to the space around it, carving paths that guide the birth of others. Even in cosmic scale, the end of one story becomes the beginning of another. Some nights, if you could watch the sky with X-ray vision, you would see our cosmic neighbourhood differently. Not black, not cold, but alive, a mosaic of faintly glowing arcs surrounding an invisible centre. Each filament would pulse with thermal energy as if breathing, and within that living sculpture the planets of our solar system would drift silently, illuminated by a light too soft for human eyes. Astronomers continue to refine this map. The Gaia data grows richer each year, the precision sharper. By tracking the motion of hundreds of thousands of stars, they can predict how the bubble will evolve. In another 10 million years, the Sun may drift out of it, crossing into a neighbouring cavity, known as the loopwood superbubble. There the pattern of formation may repeat, new boundaries, new edges, new stars. The cosmic heartbeat will continue. Speculative models go further, imagining networks of connected cavities, tunnels, where energy flows freely across light years. The local hot bubble might be one chamber in a vast interstellar labyrinth, each passage linking one stellar generation to the next. Such connections could explain why clusters of star formation appear synchronously across large regions of the sky. The galaxy may be conducting its own silent symphony, each bubble a note in the score. And yet, standing here on a small planet, orbiting a modest star, all of that grandeur feels intimate, because we are inside it. Because the air we breathe, the elements within us, the metals of our blood, all trace back to the edge of that expanding sphere. Our origin is not separate from these stars, it is entangled with them. To gaze up tonight is to look outward through the skin of the bubble itself. The light of the Milky Way's band that arches across the sky is filtered by the very material born from those explosions. We are seeing through a veil woven by supernovae, a translucent fabric of cosmic memory. What we call starlight is really the language of time still speaking from the surface of the wound. If the universe has a pulse, you can feel it here. It moves not in seconds, but in millions of years, a slow rhythm that shapes everything we are. And though we may never sense it directly, that rhythm is written into us. Our atoms resonate with it. Our existence depends on it. The stars on the surface of the bubble continue to burn young, bright, restless. Some will live long, quiet lives. Others will end in their own fiery collapse, repeating the cycle, expanding the bubble farther, writing new stories into the galactic map. Eventually even they will fade, leaving another generation to take their place. Perhaps in that endless sequence the galaxy keeps remembering itself, not through words or thought, but through motion, through heat, through the creation of light where once there was darkness. And here we are in the centre of it all, listening. A civilization of brief lives inside a structure built from millions of years of fire. We look up at the stars and think we are observers, but we are participants, children of the shock waves, travellers within the breath of dying suns. The bubble expands slowly, still 6 kilometers per second, barely a whisper by human standards, but enough to reshape eternity. Its edge moves outward through the cold interstellar medium, carving new possibilities with every passing century. What was once an event of destruction has become an ongoing act of creation. In the vast silence of space that paradox is the universe's lullaby. From chaos symmetry, from death birth, from emptiness light, and as we drift within it, perhaps the only thing we need to do is listen. Space is silent, but silence is not the same as cold. If we could feel the temperature of the void around us, if we could somehow touch the invisible matter that fills the gaps between stars, we would discover something that defies our intuition. The emptier space becomes the hotter it gets. Our solar system drifts through a region of plasma that still burns, not with fire, not with light, but with energy left behind from a time when this part of the galaxy was aflame. We call it the local hot bubble, but that name hardly captures what it is. It is not a sphere of heat one could see or sense, but a ghost of temperature 1,000,000 degrees Celsius suspended in almost perfect nothingness. At first, that sounds impossible. How can a space that empty be so hot? How can it glow with energy, yet feel like a void? The answer lies in the relationship between heat and density, between how much energy there is and how much matter carries it. In a room on Earth, air is dense enough that molecules bump into each other every fraction of a millisecond, exchanging energy constantly. That is what gives air its temperature motion shared among countless particles. But in the interstellar medium, there are fewer than one atom in every cubic centimetre. In the bubble, even less, perhaps one atom in every 100 cubic centimetres. A desert so sparse that a spacecraft could travel hundreds of kilometres before encountering a single particle. Yet each of those rare particles moves incredibly fast, carrying enormous energy. The result hot but thin. A heat that cannot be felt because there is almost nothing there to feel it. If you placed a thermometer in the local hot bubble, it would record temperatures near 1,000,000 Kelvin. But the thermometer would never warm. Its surface would barely register a change. There are simply too few collisions, too little substance for the heat to flow. It is like being inside a furnace made of dreams, hot in principle, cold in touch. This paradox gives the bubble its strange serenity. It is both a relic of destruction and a cradle of quiet. The supernovae that carved it filled it with energy, but that energy has nowhere to go. It spreads out evenly, slowly diffusing into an equilibrium so vast that it may last another 10 million years before fading. When NASA's DXL mission confirmed the bubble's existence, scientists began to measure its structure in greater detail. But it wasn't until the German eRosetta telescope launched in 2019 that the true form of this hidden landscape came into focus. Mounted aboard the Russian spacecraft Spectre RG eRosetta, scanned the entire sky in soft X-rays, revealing the texture of hot gas across the Milky Way. Its detectors were sensitive to energy levels that trace plasma around 1,000,000 degrees, precisely the temperature of the bubble. Over months of observation, a picture emerged. The sky was not evenly bright. Instead, subtle gradients appeared arcs and folds of intensity, where the X-ray light grew stronger or weaker. The pattern was not random. It suggested that the bubble is not spherical but stretched an ellipsoid pulled and deformed by time. One side of the structure extends farther toward the galactic north, the other bows downward toward the south. The northern edge fades, gradually merging into the interstellar background. The southern edge flares with energy as though still glowing from residual heat. Astronomers call this asymmetry the northern-southern gradient, and it may hold the key to understanding how the bubble evolved. The southern region of our galactic neighbourhood near the constellations of Vela and Carina is crowded with other superbubbles, remnants of multiple supernova clusters. As those cavities expand, they collide and merge, feeding energy into one another like ripples crossing a pond. The local hot bubble is being pulled by those collisions stretched along their paths, its boundaries thinned where the pressure escapes most easily. In the north, resistance from denser interstellar clouds slows its expansion. In the south, it breathes freely, opening toward the galactic halo. To map this interaction, Erosita created what is essentially a thermodynamic portrait of our corner of the Milky Way. Each pixel corresponds to a temperature, each gradient a memory of violence. The result is hauntingly beautiful, a luminous shell glowing softly in violet and blue, rippling outward, like the surface of a bubble illuminated by an unseen sun. For those who study it, this map is more than data. It's a history of energy itself. Each gradient is a line of time, each flare a story of collision. Where X-ray brightness peaks new heating is taking place probably from recent or nearby supernovae. Where it dims, the plasma cools, radiating its warmth into the vast night. Through this map, astronomers realize something profound: the Milky Way is not filled uniformly with dust and gas. Instead, it is a landscape of hollows and walls, regions of extreme emptiness enclosed by filaments of dense material. The galaxy, in other words, is more like a sponge than a disk, its structure riddled with cavities where supernovae have cleared the way. Some call it the Swiss cheese model of the interstellar medium. Our solar system happens to be drifting through one of the larger holes, and yet even here inside what seems like emptiness, life thrives. The Earth orbits the Sun in gentle warmth, protected by its atmosphere, oblivious to the million-degree vacuum outside. The heliosphere, the bubble of magnetic influence created by the Sun's wind, forms an inner cocoon within the larger one. It shields us from most of the cosmic radiation that flows through the bubble. Without that magnetic shield, the stream of high-energy particles would bombard our atmosphere, constantly tearing away molecules of ozone, disrupting life. We survive in part because of layers the Sun's bubble within the star's bubble, each guarding the smaller world inside. The deeper scientists probe, the more they see that this hot emptiness is dynamic. Its edges move, its temperature fluctuates in response to distant events. Each nearby supernova can reheat a portion of its plasma, sending gentle waves of energy through the void. Even the smallest perturbations can ripple across hundreds of light years, like faint murmurs travelling through glass. Imagine that you could drift there outside the influence of the Sun, surrounded only by this faintly glowing gas. There would be no sound, yet you might sense a pulse. Particles drifting, ions colliding, magnetic fields whispering across eternity. To human eyes, the scene would appear black, but to X-ray vision it would shimmer faintly soft blues and purples, woven together like mist caught in sunlight. At its boundaries, the bubble touches other cavities, one of them called the loop-ween superbubble, another near the Gum Nebula. Between them, thin corridors of gas seem to connect like tunnels channels through which energy and matter can flow. Scientists speculate that these channels may form a galactic network, a web of bubbles joined at their edges, each influencing the other's expansion. In this sense, the Milky Way is a mosaic of thermodynamic ecosystems exchanging pressure, heat, and radiation across immense scales. Within this network, the local hot bubble plays a unique role. Because it lies near the inner edge of the Orion Arm, it acts as a gateway between the dense molecular clouds of the spiral arm and the more tenuous regions of the galactic halo. Some astrophysicists even suspect that it channels cosmic rays, that its magnetic topology helps guide high-energy particles along the galactic field lines that pass through our neighbourhood. The emptiness we inhabit may not be passive at all. It may be a conduit of cosmic energy. When we talk about temperature in this context, we must also talk about entropy, the spread of energy through space. Every supernova that fed the bubble increased its entropy, pushing the interstellar medium toward a more uniform, less ordered state. And yet, paradoxically, that very act of chaos paved the way for new structure. By clearing the dust and heating the gas, the explosions created the conditions for balance, for transparency, for stars like the sun to shine, unimpeded by cosmic haze. Our night sky owes its clarity to destruction. Were it not for these ancient blasts, the Milky Way above would be obscured by thick curtains of dust. Instead, we see the stars with rare precision, our view sharpened by the void left behind. This is the quiet miracle of the local hot bubble. It is the reason we can see the universe so clearly, the reason starlight reaches us unfiltered. But clarity brings reflection. If emptiness can be hot, if absence can contain energy, what does that say about the universe itself? Perhaps space is never truly empty. Perhaps it's a field of potential waiting for meaning, storing memory in the very motion of its atoms. When scientists measure the temperature of the bubble, they are also measuring its history. Every photon of X-ray light we detect is a message from an electron that once felt the force of a supernova. Those photons travel across centuries across the vacuum, across our instruments, carrying the memory of their origin. The heat we record is not simply heat, it is remembrance. There is something deeply human in that realization. We too carry energy born in violent beginnings. The carbon in our cells, the calcium in our bones, were once locked in the hearts of stars. When those stars exploded, they scattered their essence, seeding the clouds that formed the sun and earth. The fire of their deaths became the warmth of our blood. The pattern repeats from cosmic scale to personal scale heat, in emptiness life from destruction. And so when we drift through this million-degree silence, we're moving through our own ancestry. The bubble is not foreign, it is familiar. It is part of the long chain of transformations that made us. Even now it continues to change. Computer simulations show that its expansion is slowing as it encounters cooler, denser regions at its rim. Within the next few million years, it may merge with neighboring cavities, forming a larger complex that reshapes the local interstellar environment once again. If another massive star explodes nearby, as one inevitably will, the cycle will begin anew. The temperature will rise, the emptiness will breathe again. It is humbling to think that such vast processes unfold quietly beyond our senses. Here on Earth we speak of warmth and cold as simple opposites, but in truth they are intertwined. The heat of the bubble, invisible and intangible, maintains the delicate balance of our galactic neighborhood. Without it, clouds would collapse. Differently, radiation would flow in other directions, cosmic rays would strike us in unpredictable ways. Our existence depends in some subtle measure on this heat that no one can feel. At night, when you look up at the stars, remember the space between them is not empty. It glows faintly with the breath of ancient suns. The warmth you cannot sense is there enfolding the solar system like a soft, transparent ocean. And perhaps that is the most beautiful paradox of all. That what seems like nothingness is in truth energy-preserved heat, without touch, fire without flame, life born from absence. In the vast quiet, the bubble still expands. 6 kilometers every second, a slow exhalation through eternity. One day it will fade, its edges merging into new forms, its heat distributed among countless other clouds. But for now it remains a million-degree whisper holding the memory of all that came before, and we tiny sparks adrift within it, float in that warmth unaware. The emptiness is not cold. It never was. The galaxy is full of holes. Not the empty kind, but the kind left behind by motion, where energy once passed, where stars once died. The local hot bubble that shelters our solar system is only one chamber in a vast and ancient labyrinth. For millions of years it has been expanding, pushing outward, until its invisible walls began to touch others, and where two bubbles meet something remarkable happens. A tunnel forms. Astronomers call them interstellar chimneys, long corridors of hot gas that link neighbouring cavities. They are not tunnels in the solid sense, but channels of lower density carved by pressure and time. Through them plasma flows freely, carrying radiation, magnetic fields and particles from one superbubble to another. It is as if the Milky Way breathes through these corridors, exchanging warmth and memory between its lungs. One of the most striking of these connections is the so-called Canis Majoris Tunnel, a channel thought to link our bubble with the enormous Gum Nebula, a faint circular glow visible in the southern sky. The Gum Nebula itself is a gigantic remnant more than 1,000 light-years wide, created by multiple supernovae and stellar winds. Where its northern edge overlaps the southern boundary of the local hot bubble, The two structures appear to merge, forming a long corridor of ionized gas. Along this passage, energy travels almost unimpeded, drifting from one ancient wound of the galaxy into another. If we could see this tunnel, it would not look like a cave or pipe, but like a pale aurora stretching across the void, a luminous fog with filaments of blue and gold glowing faintly in X-rays and radio waves. Every particle within it carries the story of two families of stars, those that exploded here and those that exploded there. The corridor is their shared memory, a bridge between generations of cosmic fire. To the north, another link may exist, a connection between the local hot bubble and the Lupus superbubble, a neighbouring cavity that lies toward the constellation Centaurus. Lupi is older, shaped by powerful explosions in the Scorpius-Centaurus association millions of years ago. Its boundary presses gently against ours, separated by only a few dozen light-years of thin gas. Where the pressure equalizes, magnetic field lines may intertwine, creating a narrow, elongated tunnel, a hidden highway through which cosmic rays can flow. Some scientists think these passages explain why high-energy particles reach Earth more efficiently from certain directions in space. The tunnels may act as cosmic conduits, guiding streams of charged particles along invisible lines of force, much like wind travelling through mountain valleys. In that sense, our entire solar system might sit beside a quiet current of galactic energy, a slow river of particles that drifts through the void around us. Visualizing such structures is difficult, but modern simulations offer glimpses. By combining X-ray radio and optical data, researchers have built 3D models showing how neighbouring bubbles interlock. They form a mosaic of cavities and bridges and intricate foam that stretches across hundreds of light years. Each bubble expands until it meets resistance, then links to others, through points of weakness the same way soap bubbles connect when their surfaces touch. The result is a galactic web of heat and emptiness, a network of glowing tunnels threaded through darkness. Speculative models go further, suggesting that these corridors could influence the very evolution of star systems. Where bubbles overlap, gas densities and magnetic fields change dramatically. That can trigger turbulence, compress clouds, and spark the birth of new stars along the junctions. In this view, the galaxy's star-forming regions are not isolated nurseries, but nodes in a larger circulatory system where every explosion and every silence is connected. It is tempting to imagine travelling through one of these tunnels. You would leave the solar system and enter a region where the temperature holds near 1,000,000 degrees, but the air is thinner than any vacuum ever created on Earth. There would be no resistance, no light except the faint glow of X-ray plasma. You would drift for centuries through a corridor wider than any human map, guided by invisible currents of magnetism. Occasionally, dust grains, tiny glowing embers of carbon and iron, would pass by, each a relic of some distant supernova. You would be moving through the bloodstream of the galaxy. If we could trace that bloodstream, we might learn how the Milky Way regulates itself. Energy expelled by dying stars does not vanish. It migrates through these channels, redistributing heat across thousands of light years. Pressure equalizes, magnetic fields stabilize, and the cycle of matter continues. The galaxy, like a living organism, balances destruction with renewal. On Earth, the concept feels abstract: plasma tunnels, superbubbles, light years. But there is a human mirror in it. We too are networks of emptiness and energy. Between every atom in our bodies lies a gulf as wide as those between stars. Yet within that emptiness, forces connect us, flow through us, hold us together. The pattern of the cosmos repeats within the pattern of our cells. When Erisita mapped the sky, scientists noticed faint arcs of brightness aligning with these supposed tunnels. They looked like strokes of watercolour laid upon a dark canvas, evidence perhaps of pathways unseen. If those alignments prove true, it means the bubble around us is open, breathing, exchanging energy with its neighbours. We are not sealed inside an isolated cavity. We are part of the Milky Way's vast circulatory system. The speculation continues. Could these tunnels act as shortcuts for radiation, or even for future spacecraft using magnetic sails? Could they reveal something fundamental about how galaxies vent their heat into intergalactic space? Each possibility opens another door, another corridor of thought. But beneath the science, the feeling remains awe at the quiet design of chaos. We inhabit a structure built by destruction, and yet that structure is graceful, balanced, alive. Every supernova carved a new room in this cathedral of plasma. Every collision opened a new hallway. Through them, light still travels, echoing the soundless hymn of the galaxy. If the universe had arteries, these would be them. and somewhere within that vast glowing anatomy drifts a small planet of oceans and breath, listening, learning, unaware that it too is part of the flow. So tonight, when you look into the darkness, remember that darkness has corridors. Invisible pathways stretch from our sky to distant nebulae, linking the history of dying stars with the birth of new ones. We live not at the centre of anything, but along a bridge, a small bright point suspended between the past and future of light. And through that bridge the Milky Way continues to breathe. There is no true silence in space. Even when every sound is gone, the light itself still hums a faint vibration of memory, a resonance that carries the story of stars. Everything that lives in some form was once a spark of that story. Stars are born in darkness. They begin inside cold molecular clouds, immense cocoons of hydrogen and dust. Within those clouds, gravity pulls gas together grain by grain, forming dense knots that grow heavier with every heartbeat of time. When pressure becomes unbearable, the atoms inside begin to fuse, releasing light, and from the depths of that darkness a new star ignites. It seems like a miracle, but it is a pattern the universe transforms collapse into creation, and yet nothing that burns forever survives forever. A star's life is a balance between two opposing forces, the inward crush of gravity and the outward push of energy from fusion. For our sun, that balance has lasted billions of years. But for massive stars, the balance is fragile and brief. They shine too fiercely, burning through their fuel in only a few million years. When their energy runs out, gravity wins. What follows is death, but not an ending. When the core collapses, atoms are crushed so tightly that protons and electrons merge into neutrons, releasing a shock wave of unimaginable force. The outer layers are blasted away in an explosion that outshines an entire galaxy for a moment, a supernova, and in that instant of destruction, the universe is enriched. New elements are forged: oxygen, silicon, iron, gold. Everything solid, everything real begins here in death. Our bodies are made from this. The calcium in your bones, the iron in your blood, the carbon in your cells. Each atom was born inside a dying star. We are in a literal sense the dust of supernovae held together by memory. When you breathe, you're completing a cycle that began millions of years before the Earth itself formed. That is why astronomers say we are the universe becoming aware of itself. After a star explodes, what remains depends on its mass. A smaller giant may leave behind a neutron star, a sphere no wider than a city yet heavier than the sun. A larger one collapses completely, forming a black hole, a singularity where gravity bends space and time into silence. Around those remnants, the expelled gas expands into bright nebulae clouds of glowing debris that drift for millions of years, spreading heavy elements through the galaxy. In time, those elements mix with colder clouds where gravity will again sculpt new stars. The cycle continues. In the local hot bubble, this rhythm has repeated again and again. 15 ancient supernovae cleared the space we live in, then triggered new waves of star formation along its edges. The same shock waves that destroyed one generation gave birth to the next. The bubble breathes contraction and expansion, death and creation. Some of those newborn stars now shine in constellations we know by name: Scorpius, Lupus, Corona, Australis. They are the children of that ancestral fire. Each will live its own brief life, then end in its own blaze, feeding the galaxy again. In the grandest sense, the Milky Way is alive through this repetition, each heartbeat measured in millions of years, each breath a supernova. From this perspective, time itself changes meaning. To us, a lifetime is a flicker. To the galaxy, it is one note in a continuous song. The light of stars, the dust between them, the energy that moves through tunnels and bubbles, all of it forms a chain, a self-sustaining orchestra of renewal. Theoretical models describe this cycle in terms of feedback. When stars explode, they heat and disperse the gas around them, preventing more stars from forming too quickly. When that gas cools, gravity gathers it again, and the process restarts. Too many explosions and the galaxy would thin itself into emptiness. Too few, and it would collapse under its own weight. Between those extremes lies harmony, a dynamic equilibrium sustained by destruction. Every supernova is a kind of correction, a recalibration of the cosmic balance. Even the smallest burst of light contributes to this universal rhythm. There's a deeper poetry hidden in that mechanism. In the human mind, we fear endings. We see death as absence. But in the language of the stars, death is simply transformation. the release of matter back into potential. Every collapse is a prelude to another beginning. Even black holes once thought to be eternal prisons now seem to leak energy, over unimaginable time returning what they took. Nothing is ever truly lost, it only changes form. If you could watch the galaxy in accelerated time compressing millions of years into seconds, you would see waves of light blooming and fading like bioluminescent tides. Each bright flare marks a star's death. Each dimming cloud marks its rebirth. You would realize that the Milky Way is not static but alive, pulsing, breathing, learning how to maintain itself. The energy that drives this process comes from fusion, the simplest act of creation in the universe. Two atoms merging into one, releasing energy as light. That same light warms our planet, fuels our ecosystems, and gives rise to consciousness itself. When we look at a candle or the sun or even a screen glowing in the dark, we are seeing echoes of that same principle, energy becoming form, dissolving back into energy. In that way, every heartbeat, every thought is a continuation of the stellar cycle. We live within it, and it lives through us. Astrophysicists estimate that our galaxy produces and destroys about 3 stars per year. At any given moment, hundreds of millions are dying, and hundreds of millions are being born. The balance is held for billions of years. It is an eternal recycling system, efficient, graceful, inevitable. One might ask, where does it end? Does the universe eventually run out of material to renew itself? The answer, at least for now, is no. The dance continues. Matter circulates, but energy disperses, cooling the cosmos slowly, steadily. One day, far in the future, the universe will reach a state of quiet equilibrium, when every star has burned out, every bubble has cooled. But that is a destiny beyond imagination. For now, the fire still burns. Here inside our bubble we live during a calm between storms. The stars that gave birth to this region are gone, and their children have not yet died. We drift through the aftermath, a rare, peaceful moment in a cycle of otherwise endless violence. It is a fragile grace, but a real one. Perhaps that is why the night sky feels so sacred. We are witnessing light that has survived every stage of the cycle, the fire of birth, the shock of death, the drift of dust, and the return of flame. Each star is a note in a song of continuity, a reminder that energy never truly sleeps. If we listen closely enough, we can almost hear it, the faint, patient rhythm of the cosmos breathing. It is the rhythm that built us, the rhythm that sustains us, the rhythm that will one day reclaim us. And as the universe turns, we turn with it particles of dust, sparks of awareness, fragments of dying suns dreaming themselves alive. Every particle remembers, not in the way humans remember with thought or feeling, but in motion, in the subtle record of its journey. Every photon that leaves a star carries the story of where it was born, how hot that place was, how dense, how violent, and how long it has travelled through the sea of space to reach us. In this sense, the universe is a vast archive. Each atom, each wave of light is a letter written in the oldest language of all physics. And when we look at the night sky, we are reading it. The Milky Way itself is a library of memory. The oldest stars near its centre have witnessed the galaxy's youth. They burn dim and red, their chemistry different from the newer stars along the spiral arms. In their atmospheres, astronomers find traces of the first heavy elements forged by the earlier supernovae. The ratio of iron to hydrogen, the abundance of lithium, the spectral fingerprints of oxygen and carbon, each acts like a timestamp, revealing how many generations of stars preceded them. It is through this stellar archaeology that we reconstruct the galaxy's past. Light is the messenger. When a photon leaves a star, it begins a silent journey across millions of years. It passes through dust clouds, magnetic fields, and the expanding fabric of space-time itself. By the time it reaches our telescopes, it has been stretched, reddened, scattered, but never erased. Even the faintest glow from a distant galaxy is an echo of an event that happened long before Earth existed. To look far is to look back. The farther we see, the older the memory becomes. Cosmologists sometimes call this the look-back time, the idea that distance and time are intertwined. When we observe a quasar 10 billion light-years away, we're not seeing where it is now, but what it was when the universe was still young and wild. Every observation is a form of time travel, a communion with the past through the language of light. But memory in the universe is not just written in photons. It's encoded in the distribution of matter itself. The cosmic web, the network of filaments that stretch between galaxies, still bears the imprint of quantum ripples that existed less than a trillionth of a second after the Big Bang. Those ripples' tiny variations in density grew over billions of years into galaxies and clusters. Every structure we see today is a magnified echo of those first fluctuations. The universe has never forgotten its beginning. It has only expanded upon it. In the quiet of night surrounded by the black ocean of space, it's easy to imagine the universe as something distant, indifferent, eternal. But when we study its memory, we find something else: continuity. Every particle we measure, every ray we detect, connects us to everything that has ever been. We are not separate observers. We are part of the memory itself, on the most intimate scale that truth becomes almost sacred. The hydrogen in your body, the atoms in the water you drink and the air you breathe was created during the first 3 minutes after the Big Bang. Those same protons have existed for over 13 billion years, surviving stars' collisions and the drift of time until finally they became part of you. In this sense, you're not only made of stardust, you're made of history itself. Perhaps memory is not something the universe holds, but something it is. Every movement, every vibration, every line of energy across the void is a continuation of what came before. From that perspective, time is not a river flowing forward, but a spiral winding endlessly through transformation. The cosmic microwave background, the oldest light we can see, is another kind of memory. It is the faint afterglow left from when the universe was only 380,000 years old, the moment it first became transparent. We can still detect that glow today, a whisper of heat, stretched into microwaves by the expansion of space. It fills every direction, equally a soft reminder that the universe once burned everywhere at once. Astronomers use this ancient radiation like a photograph, a snapshot of the cosmos in its infancy. Tiny differences in its temperature, mere millionths of a degree, reveal the seeds from which all future galaxies grew. To gaze at that background is to look at the universe's first memory, its earliest breath still echoing across eternity. And yet as we look deeper, something more human arises. If the universe remembers everything, every explosion, every photon, every vibration, then perhaps consciousness itself is another form of memory. We are the universe reflecting upon its own story, organizing chaos into awareness, turning data into meaning. Our curiosity is the cosmos learning to recall itself. When you close your eyes and imagine the stars, you're participating in that act of remembrance. Your brain, made from atoms born in supernovae, is replaying light that left its source long before humanity began. Every thought about the universe is in a way the universe thinking about its own existence. Perhaps that is why silence feels so full. It carries echoes of the Big Bang, ripples of gravity, and the hum of ancient light that never truly fades. In that silence there is memory, and in that memory there is us.